Thanks for joining us for today. This is the second in a two-part series on teaching predictive modeling. On Tuesday, we talked about teaching basic predictive modeling. So this was an introduction to JMP for modeling, and in particular, we talked about data preparation for modeling. So we saw some of the things that need to be done to prepare data for modeling, including compiling data. So we briefly mentioned things like using a query builder to pull data into JMP, accessing data via SAS. These topics are covered in depth in a previously provided webinar. And in fact, our webinar library is where we post all of our webinars that we provided in the past. So there's a new webinar that's been posted, Preparing Data for Analysis. And this talks a lot about dealing with missing values, recode, and also using the query builder to compile data. On Tuesday, we also talked about data exploration to get to know our data. So these are some of the key platforms that we talked about. We talked about how to derive new variables, so things like transformations, instant transformations by right-clicking on columns, either in the platform or the data table. We talked about using recode, which is very nice for cleaning up categorical data. And we saw a couple of other functions for deriving new variables. We spent a little bit of time talking about missing values and outliers. We provided an overview for tools for reducing dimensionality. And in our example, we talked about using hierarchical clustering, but there are a wide variety of tools available. And we also saw how to partition our data for modeling. So we saw how to create a partition of our data into training, validation, and test sets for use in modeling. And for this, we use the utility to make a validation column. The example we saw is actually in our sample data directory. So under the help menu, if you go to sample data library or sample data under exploratory modeling, you'll see this example equity. And I'll post this journal along with some data sets. And this is a really nice data set to explore different issues you run into in terms of data quality and the different tools in JMP for dealing with those issues. So again, I'll post this. This webinar and the previous webinar will be posted in our webinar library under Teaching Predictive Modeling with JMP Pro. In fact, you'll see previously provided versions of these webinars. There was a shorter version that didn't go into as much depth that's posted there now. So what are we going to talk about today? So today we're going to get into some more advanced tools and algorithms that are typically covered in analytics courses and courses in predictive modeling and data mining. So we're going to see how to build trees or use tree-based methods. In fact, we call this recursive partitioning. The platform name is partition. So we'll see how to build a classification tree and a regression tree. And in JMP Pro, which is the version of JMP available to most universities, and what I'm using here, you can also use Bootstrap Forest and boosted trees. So we'll see how to construct these and also how to interpret the results. We'll talk about building neural networks. We'll see how to build generalized regression models. In JMP, this one platform can be used for both fitting models, linear models with non-normal response distributions, but also for fitting penalized models. So for example, Lasso and Ridge and Elastic Net. And then we'll cover some special topics. So we'll see how to set the random seed. Many algorithms in JMP have a random start. And the platforms include the ability to set the random seed, but there are some platforms where setting the random seed is desirable, particularly if you're teaching and you want reproducible results for your students. So we'll see how to set the random seed. We'll talk a little bit about how to model in cases where we have a classification situation and we want to model unbalanced data. So there are fewer observations in the target category than there are in the non-target category. So we'll see some ways of addressing this. We'll talk about how to change the cutoff for classification, and we'll see how to integrate cost using the profit matrix. And there are a series of add-ins posted in our user community, and I'll show you how to find these. If time permits, we'll also talk about how to use the new Text Explorer platform for visualizing, preparing, and analyzing unstructured text data. So why don't we go ahead and get started, and I will tuck this window away. And I want to start by talking about recursive partitioning. And one of my favorite tools for introducing this topic or one of my favorite data sets, is Titanic passengers. So Titanic passengers is available in the sample data directory. And my response that I'm interested in, my mouse is sticking, is this column survived. And since we haven't really seen this data in depth, we introduced it in the first webinar. Let's take a quick look at this. So I'll use distribution just to give us kind of a high-level view of the key variables in the data set. And I'm going to unstack the variables. I have a preference set. So survived, yes and no. Yes is the passenger survived. No, they did not survive. And this dynamic linking allows us to explore potential bivariate relationships. So for example, with yes highlighted, we can see that a majority of the females, or a much higher percentage of the females survived than males. We can also see the breakdown of those who survived across the passenger classes, different ages, and some of the other variables. If I take this a step further and look within fit y by x, fit y by x can be used for bivariate analyses. So here we can get regression, one-way ANOVA. My response here is survived. So if I put survived under response, I'm going to have the ability to either do a logistic regression or contingency tables in chi-square. And I'm using this more from an exploratory purpose. So I'm going to look at survived versus passenger class, age, or sex, age, and these other variables as well. Notice that target level appears. So one of the possible analyses, survive versus age, which is continuous, and survive versus siblings and spouses, is logistic regression. So we can specify what the target category is. And I want to model the probability of yes. And again, we're doing this really just from an exploratory perspective. So if we're looking at the contingency table breaking down passenger class by whether they survived or not, the legend on the side is essentially a stacked bar chart. So we can see that far more passengers did not survive than survived. And in any graph and jump, if you hold your mouse over the graph, you'll see the values. The width of the bar for 3 indicates we had far more third-class passengers than first and second. And we can see within third-class passengers that a lot more of the third-class passengers did not survive. We see similar results for male versus female. And I want you to keep this graph in mind. When I'm using partition analysis or introducing partition analysis, I've often first used this data set, and this graph is very similar to what we'll see in partition. So keep this in mind. As we scroll across, we also get a glimpse at what logistic regression looks like. So let me close this, and I'm just going to quickly fit a regression model, a logistic regression model, using fit model with, again, survived. And I'm going to select just some key variables here. In fact, I'll just select a subset of the variables, and I'll use factorial to degree to add in interactions. Again, I want to model the probability of surviving, so yes, and I'll click Run. So this is logistic regression. And least squares regression, you may recall, looks very similar. We have an effects summary table. We have a whole model test. It's called ANOVA if we have a continuous response. We see the parameter estimates, so these are the terms in our logit. And just to paint a picture and set the stage for partition, I'm going to use the profiler. So the profiler allows us to explore this model that we've just built. And it's really nice, particularly in a logistic regression situation when we have interactions, because it gives us the ability to dynamically explore our coefficients, but also the nature of these interactions. So here I'm starting off where I've got first class passenger that's a female that's roughly 30 years old, and the survival rate is about 96%. The slopes of the line tell us what happens to the response, probability yes, as I change the values of each of the x's. So if I drag this person to a second class and then third class, we can see what happens to the probability of survival, but more importantly, we can see what happens to the slopes for the other lines. So if this person were a female versus a male, notice that the slope of the line changes dramatically. And in fact, if this person were a third class male, age is important, and it appears that only younger males had a higher probability of survival. So keep this picture in mind as we talk about partition. So the partition platform in JMP is under predictive modeling. And again, this is recursive partitioning. So we're going to build a decision tree. Our response is survived. And since survived is categorical, we're going to fit a classification tree. If our response is continuous, we'll fit a regression tree. And the mechanics are very similar. So what I show you here is going to be very similar to what we'll see when we fit a regression tree in a few moments. So my response is survived, and I'll select the same key variables. And for now, I'm going to do this without validation. This is just to introduce the idea of what a decision tree is. There are a couple of options on the side. Informative missing, most of the platforms in JMP have a way of dealing with missing values called informative missing. In the partition platform, if I have a categorical variable that's missing a value, a new category called missing will be created. If a continuous variable is missing a value, JMP will try to split the data into two subsets where it assigns the missing value to either side of the split, and it picks the side that in this case forces the probability of survived as far apart as possible. So the algorithm as a whole, what it's going to do is it's going to search through each of the variables that we've selected, and it's going to pick the variable that forces the probability of survival as far apart as possible. So I'm going to click OK. And this plot may look somewhat similar to what we've already seen, but let me make a few changes. I'm going to turn off the points. So this should look like what we saw in the legend in fit y by x, where we've got the breakdown of no versus yes. And I'm going to add, under display options, show split count. So this gives us our starting values. So if we had already talked about the breakdown of yes versus no in distribution, these are the same exact numbers. So what is the decision tree doing? I'll open up this candidates box, and what a decision tree is going to do is it's going to search through the variables, and it's going to find every single value for each variable where we can subdivide the data into two subsets. And it's going to test the difference in the probability between the two subsets. So you may recall that passenger class has three categories, first, second, and third. It's also ordinal, and there's an option in the dialog that said ordinal restricts ordering. So there are two possible ways that we can split the data into two subsets on passenger class. One side can be based on first class passengers, the other on second and third, or we can have first and second class passengers combined in one subset and third class in a second subset. So it does that for passenger class. For sex, there's only one way to divide the data into subsets, male versus female. For age, it's going to test all possible ways we can subset the data based on age. So age is continuous, same with siblings and spouses and parents and children. And for each one of these, it's doing a hypothesis test. Now, since we're artificially inflating p-values or deflating p-values because we're trying every possible way to split the data, we're going to use a log worth instead of a p-value. And a log worth is the negative log 10 p-value. And the way we use this is the higher the value, the more significant the split. And we're using this candidate g-square or this likelihood ratio chi-square statistic to tell us where to split the data. There's a little asterisk here indicating that our first split of the data into subsets is going to be on sex. So if I minimize this and click split, here's our first split. And we read this as a logic statement. If sex equals female, the probability of survival is 72% or roughly 73%. If male, then it's roughly 19%. Now this process continues, and it continues until there's only one observation in each of the nodes. So my next split will be based on either passenger class or age. And in this case, it's going to split under female for passenger class. And at this point when I'm teaching, I typically ask my students, think about what we saw in logistic regression. What were the most important variables? At which value might it split? And it paints a pretty clear picture of what the algorithm's doing. So if I click split again, this time it's split on passenger class for females. So first or second class females have a pretty high survival rate. Third class females, it's quite low. My next split is on male. And in this case, if males are greater than or equal to 10 years or missing, the probability of survival is only 17%. But if it's less than 10 or not missing, then the probability of surviving is about 58%. So what we've just done here is built a logic statement, and the fact that these splits are on different variables is an indication of potential interactions. So age is important, but only for males at this point. Passenger class is most important for females. Now to get some summaries of what we've done, we can look at the leaf report. And the leaf report gives us a summary of what the model's doing. Our model here is simply going to predict if female and passenger class is first or second, it's going to report out this result. In fact, if I save out the probability formula, I'll go to Save Columns, Save, in this case it's called Prediction Formula, and I go to the table, and I've got now 3 new columns. I've got probability survived, no, yes, and most likely survived. If I right-click on this, this is a stored formula, then we can see that logic statement. If sex equals female and passenger class is first or second, this is the rate. So this model is only capable of predicting a few values. Let me go back to that window. Now some other tools that I like to use here as I'm growing my trees, there is a tool called column contributions. And when you're building a really big tree, this is a nice way of summarizing the most important variables. So the only 3 variables that appear in our split so far are sex, passenger class, and age. And this likelihood ratio chi-square is very, very large for sex, indicating that sex explains most of the information. And since this is a classifier model, we can ask for an ROC curve. We can also ask for a lift curve. And there are lots of other tools. One thing that I do want to mention is I could continue to split this model. So if I keep hitting split and split and split, it'll split until there's not enough information to continue splitting. So one of the considerations is how do we control overfitting? If we simply continue to split, this model will be vastly overfit. So one tool is to specify the minimum split size. Basically to tell JMP if there are fewer than 5 observations in any one of these nodes, then don't split. Don't consider that a candidate for splitting. A second way of dealing with this is using model validation. So we're going to talk about model validation in our next example. So let me go ahead and close this. And again, this data set is available in the sample data directory. So we're going to revisit an example that we saw in the first webinar. This is data that was downloaded from the cityofboston.gov, and I'll just run some of the save scripts I have in the corner to facilitate things. So these are data, and this is a map produced from the graph builder, and I've asked for a connection to OpenStreetMaps. So let's take a look at these data. Now I live north of Boston, and South Boston is a neighborhood south of downtown Boston that is up and coming and has a lot of homes for single-family homes and young professionals. And I've colored these points by using hierarchical clustering. So I've clustered based on latitude and longitude to give us different regions within this neighborhood. So the modeling situation is that I want to model the total value as a function of a lot of these other variables. So I've got things like gross area, the number of floors, the number of rooms, bedrooms, baths. In fact, let's go ahead and look at these variables. And I'll go ahead and stack these guys, or unstack them. So my total value, most of these are between $330,000 and $486. I can see the gross area. So this gives me an indication of kind of the middle values, the number of floors, the number of rooms, the number of bedrooms. So I'd already done quite a bit of data prep for this data. I used Graph Builder to explore relationships between the x's and the response total value. And I'm using column switcher here, which is a function at the top of the data table or under the red triangle, to basically scroll through my different x's to dynamically just swap out each of the x's on the x-axis. So it facilitates the data exploration process. I did the same thing for my categorical variables. So here's building style, here's roof type, here's heating type, and I can see some relationships there. And here's that clustering variable where I used hierarchical clustering to group homes based on latitude and longitude. So it looks like there might be some differences. I would also use this to explore potential interactions. So when we fit a least squares model, actually before I did that, I also looked at correlations. When I look at correlations between my x's, I'm interested in looking at correlations between my response and my predictors. So here I see there's a pretty strong correlation between total value and gross area, but I'm also interested in looking at potential correlations between each of the predictors. So for example, if I look at gross area versus number of rooms, it appears that they are correlated, and the numbers are all stored in the correlation matrix up above. The way we represent correlations graphically is through a density ellipse. And the tighter this ellipse is to a line, the stronger the linear association. So we can see the number of rooms and number of bedrooms, as expected, are highly correlated. The gross area and number of bedrooms are also correlated. So this can lead us to issues if we're fitting a linear model where we have collinearity or multicollinearity between our x's. And we'll see that the generalized regression platform gives us some tools for dealing with this. So a regression model that we fit, I fit this using the same platform, fit model. And in this case, I'm going to use validation. So what I'd like to do is I'd like to build a model for total value. And validation, I used in advance this make validation column platform or utility to partition my data into subsets, training, test, and validation. So by putting validation in the validation field in fit model, what I'm telling JMP to do is build my model only using the training data, validate it or tell me when to stop growing it based on the validation data, and then hold out the test data so that I can select from competing models when I get to that point where I've built enough models. So when I hit run here, JMP allows me to take a look at the variables that are significant and reduce this model. So we saw this before. So if I remove these one at a time, and I'll do this a little bit more quickly, I can see some things that are significant. So gross area is highly significant. Clustering here is also significant. The number of baths and fireplaces are significant. Now, once I have a model like this, I saw last time that I can save the formula to the data table. So if I go to Save Columns and then Save Prediction Formula, this saves the prediction formula to the data table. But if I'm ultimately interested in building a number of competing predictive models, I might want to store this out so that I have it in a report where I can compare this easily to competing models. So there's a new option in JMP 13, and it's called Publish Prediction Formula. When I publish prediction formula, this writes the formula out to a formula depot. And what this allows me to do is I can save the script out. So if I hit run script, this is actually a standalone report. So if I have data that I want to score that's in another data set that has the same variable names, I can run the script and it'll score new data. I can also use this to pull in work that I've already done in my data table. So I can pull in formulas if I've derived new variables. I can compare this model to competing models, and we'll see this in a few moments. And I can also write out scoring code in a variety of different languages. And I'm going to build some more models, but we're going to come back to this, so keep this in mind in a few moments. Oops, let me leave this open. I'm going to hit cancel and just leave this guy open. All right, so this was a linear model. So we already saw how to build a partition tree. We'll do the same thing here. And since we have a continuous response, we'll be building a regression tree. So I'm going to populate this using the same variables, use validation. When we have a categorical response, JMP is trying to find splits that maximize the difference between probabilities. In this case, we're going to find splits that maximize the difference between the means. Now, since I have validation here, we can automate this process of finding the optimal tree. And again, we have those same two options down below that I'll keep turned on. So let me click OK here. And instead of seeing the probability or the starting probability, here we see the overall mean. So this is the grand mean. And again, I see the candidate. So all the language is pretty much the same. For a categorical response here, we saw the likelihood ratio chi-square. Here we see the sum of square. Again, we see the log worth as a measure of the p-value, and we're looking at the higher the value, the more optimal the split position. Now, I could split this one at a time, and if you remember back to the linear model, the most important variable was gross area. And again, I could continue to split until I reached my minimum split size for each of these different nodes. And since I have a validation column, I'm tracking results on that validation set. And if I click the Go button, we've automated this process. So JMP will continue to split until it finds the maximum value for the validation R-square. And it pops us right down here to the split history. What the split history does, and let me zoom in on this a little bit, is that it's keeping track of the R-square for each of our partitions of the data. The blue line represents the training data, the red line represents the validation data, and the orange line represents the test data. So what the model does is it'll continue splitting until it finds the maximum value for the validation R-square. And then it'll continue splitting for 10 additional splits. And if it sees no improvement beyond that maximum value, it'll prune the model back to that point. So this line at 17 splits is our final reduced model. So that's the model that gives us the maximum validation R-square. Now JMP doesn't use the test set in any way, but it simply plots what's going on R-square for the test set in the same plot. Now I kind of like this in the classroom environment because it really paints a picture of what happens as I continue to split for my training set. Notice that the R-square for my training set keeps improving. But for my validation set, it hits a point here and then it sort of declines and just sort of bounces around. So by continuing to split, we're not actually building a model that is explaining structure in our data. So we're not improving our performance of our model by continuing to split. So that's really the value of having validation or a holdout set. It gives us an assessment of whether the model is actually fitting structure or if it's just fitting noise. Okay. So for this model, we saw earlier that we can summarize this model using the leaf report. And in fact, I'm going to summarize using column contributions. So the column contribution report, as we saw earlier, gives us a summary of where most of the splits occurred and also how important those splits are in explaining information, explaining variation in the response. And the most important variable, as we saw, is gross area. The second most important here is cluster, and this agrees to some extent to what we saw in the linear model. So we see our top variables, and sometimes we'll see a little bit of switching around in places for some of these variables. Now, if I look back at my tree, notice that gross area is a dominant split. When we have a continuous response and a continuous predictor that's highly significant, we tend to see splits that continue across that one continuous predictor. Now, the problem with this is that wherever that first split occurs, that dictates all future splits that might take place. So there are a couple of other tree-based algorithms that we can use in addition to a straight decision tree. So we're going to keep these numbers in mind. And again, we can save this out to our formula depot using save prediction formula. And I've got a version that I previously saved. So I'm going to simply close this. And let's take a look at different tree-based methods. So this was a partition tree. And there are two other options, Bootstrap Force and Boosted Tree. So I'm going to ask for a Bootstrap Force. And it's essentially the same platform. So if I hit recall here, it'll pull back in everything that I did last time. And I'm going to click OK. And this takes us to a dialog window. So what a Bootstrap Forest is we're going to build a forest with several trees, a lot of small trees that we call weak learners. And our final predictive model is going to be an average of all of these individual little trees, all these individual little models. For pedagogical reasons, sometimes I'll start here and say, well, let's start with a really small forest. Let's say we've only got 3 trees in the forest. JMP is going to randomly sample from our predictors, a certain number of predictors. It's also going to randomly sample, it's actually going to bootstrap sample a certain percentage of our observations, so we can change these. And these can be really useful if we've got, for example, small data sets with a lot of variables. I often will change this. We can also specify the minimum splits per tree. I'm going to build some really small trees in a really small forest. So I'm going to say that I'm going to have 3 trees in this forest where my maximum number of splits per tree is 5. Now there's some options on the side. You can try different combinations of these options. And the way we do this is through a tuning table. So if you have a tuning table where basically you have different combinations of these, it'll try all combinations of those. And we don't have time to go into it here, but the way I design a tuning table is I generally go to DOE. So space filling design will try to cover the entire design space. So as long as your predictors that you build in the space filling design match the names that you have here, it'll give you a tuning table and it'll try all possible combinations when you run this. Now, for pedagogical purposes, if you want your students to get the same exact results that you have here, then turn off multi-threading. Multi-threading allows the algorithm to be much more efficient. And then specify a value for the random seed that all of your students use. So if your students have the same setup, this will allow for reproducibility or repeatability across all of your students. So I'm going to, now normally I would have a much bigger forest here, but just for illustration, I'll go ahead and click OK. And what does this forest look like? The forest is essentially a collection of trees. And since I specified that I only wanted 3 trees in the forest, I've got 3 trees. And it's randomly sampling from my predictors, and it's also randomly sampling from my observations. So my first tree is full bath, then roof type, then heating type and cluster. My second tree split on full bath and then gross area. And then my third tree split on gross area and then heating type and then gross area. Now the value of doing this is where we do have a really significant continuous predictor, that remember that that first split dictates every other split that happens from that point forward. So this allows other predictors to enter into the model. Oftentimes what we'll see from this approach is that the model has much better predictive ability because we're including more information, we're including more predictors. In fact, for our little small tree here, our small forest here, gross area is still important, but now we see that we have these other predictors that have entered the equation. So this is a Bootstrap Forest. And what is a boosted tree? So the third tree-based method is called the boosted tree. And again, I'll hit recall and then OK. Now what a boosted tree is I'm going to build a narrow tree, a small tree, and then I'm going to calculate the error left over from fitting that tree, and I'm going to fit another tree on top of that. So for each iteration of this, we call this a layer. So I'm going to build a layering of small trees. And again, I can define the number of splits per tree. The learning rate dictates how quickly we converge on a solution. We can dictate the minimum split size. And we've added stochastic gradient boosting here where we can sample as we can in Bootstrap Forest. We can randomly sample from our variables, and we can also randomly sample from our data. Again, we can specify a tuning table if we want to be able to try a bunch of different iterations of this. And again, for repeatability, I'll specify the random seed and click OK. So this is a boosted tree, and we often find, since we're continuously trying to explain as much information as possible, that these algorithms perform quite well compared to other algorithms. And I haven't really been talking about this R-square. We're going to revisit R-square and root mean square error for all of the models we've been building when we get to the end. So ahead of time, I saved all these models out to the Formula Depot. So let me go ahead and close this guy. All right, so that's the tree-based methods. Now what about neural networks? So under predictive modeling, you can easily fit neural networks. And I'm going to fit the same model. Oops. Remove all these guys here. So I'm modeling total value as a function of these predictors. And I've got cluster. And neural networks require validation. So if you don't specify validation here, it'll automatically use, I believe, holdout validation when you run the model. I'm going to turn on informative missing to be consistent with the other platforms and click OK. So what we can do with neural networks are highly nonlinear models that are constructed of, and I'm just going to click Go here to show you a diagram. They're constructed of an input layer, which is all of our x's, a hidden layer, and the hidden layer has a specified number of activation functions, or a specified number of nodes with certain activation functions, and then an output layer. And the model launch dialog guides us or allows us to specify what type of model we want to build. So we can have up to 2 layers, and we can have up to 3 different activation functions, and the numbers we specify tell us how many nodes of the given activation function we can specify within each layer. So if I specify this model, well, I'll go ahead and hit Go. We can see what this one looks like. So these are highly parameterized models. So this one, I've got two hidden layers. The first hidden layer are the original 3 nodes with the one activation function each. And here I've got 3 of each of the different activations functions. So the way you read this when you're specifying this is that first layer, this is the layer that's closest to our output layer. Now our final model is simply a linear combination of output from our hidden layer. And to get a sense for how highly parameterized these are, if I look at the estimates, so this is the estimates for my second model, we can see how highly parameterized this model is. But they tend to do a very, very good job with prediction. So if we're looking at things like R-square and root mean square error, we can compare performance for this model to a more complicated model. And in general, we'll see improvement in our more complicated model. If we don't see improvement in these statistics for the more complicated model, that's really an indication that we really don't need that extra complexity. Now, a caveat for using neural networks is that they're really the ultimate black box. So in and of themselves, we're including all of the terms, and we have some nonlinear functions. So it's very difficult to explain to an end user what a neural network is doing. There is a really nice tool that helps us to understand this under Profiler, and this is the same profiler we've seen. So we can look at the prediction profiler and notice how some things get kind of bendy and curvy. So these are highly nonlinear models. But to get an indication for which of the predictors are actually most important in this model, and you can do this from the prediction profiler from any platform, we can use this option, assess variable importance. And if I can assume that there are independent uniform inputs, I'm going to select this first option. So if we can assume that the distributions are independent, I'll go ahead and click this option. And what it does is a simulation. So it's trying to isolate out the effect of each of the predictors where it's randomly distributing or simulating values that are random uniform for all of the other values. And this allows us to pick out, for example, gross area is the most important, fireplace followed by cluster, and we can see similar results. Now, in some cases, you can use this to try to identify what the key X's are to input into another model. But by themselves, neural net models are generally black boxes that are difficult to explain and interpret. So let's move on, and I wanted to talk a little bit about penalized regression and the generalized regression platform. So if I click recall here, in fact, I'm going to add some interactions. So let me add in interactions between all of our continuous predictors. So I'm going to select those continuous predictors and ask for factorial to degree. Now remember that we had some collinearity between some of these x's. And when we have multicollinearity in a regression situation, this tends to inflate our coefficients and also inflate our standard errors. In that case, instead of using standard least squares regression, I might use the generalized regression platform. And this does a lot of things for us. Under distribution, the default distribution is normal, so this would fit a maximum likelihood model that's equivalent to least squares regression. But it can also fit other response distributions. So I can do survival analysis or quantile regression, all from here. I'll keep it on normal. If I have a categorical response and select binomial, this will do logistic regression. So I'm simply going to hit run. And my initial model is simply a least squares regression model. It does something a little bit different with our coefficients. If you recall back, if you saw the first webinar, when we code or we create indicator variables or we do parameterization for our categorical variables, in fit model, JMP uses the average as the reference value. In generalized regression, it uses the typical highest level as the reference value. So it uses the typical indicator coding rather than the effect coding that we use in fit model. Now the other thing it does is it gives us a lot of different options here. So standard least squares is the default. We can do forward selection, Lasso, Elastic Net, and Ridge, and also double lasso. These are penalized methods where we're applying a penalty. Lasso and Elastic Net also do variable selection. If we've got interactions, we can also do a two-stage forward model. So let me, for illustration, select forward selection. And I've got a validation column. I'm going to click Go. And I really like this for teaching purposes because it allows us to see what happens to our model as we add additional terms to the model. So we see the original parameter estimates. And if I start with nothing in the model, in fact, I'm going to go ahead and turn on a residual plot. I'll plot the actual by predicted. Okay, so if I turn on a residual plot where I have nothing in the model, my model simply predicts the mean. These lines here represent coefficients, and they represent the magnitude of the coefficient as I add additional terms to the model. So my first term to enter the model, if I look into parameter estimates, is, as we'd expect, gross area. Now, as I add additional terms, notice that that parameter estimate actually shrinks. It decreases. And I can keep an eye on what happens to these residual plots as I add additional terms to the model. So as I add terms, notice that my residual plot for my training set is getting tighter and tighter, but I can keep an eye on what's happening to the validation and test set. So we call these solution paths, and the solution path on the side is giving us an indication of our best model using the scaled negative log likelihood statistic. So the black line represents what happens with our validation set. The gray line represents what happens with our training set. And we can see that there's a point where we get the minimum value on our validation set, and then it starts to increase. So if I go much beyond that point, if we keep an eye on the validation and test residual plots, notice that points just sort of move around a little bit, but things don't really change. If we've got a lot of collinearity, for example, maybe I start adding terms, we'll often see these lines just skyrocket. So this gives us a nice way of exploring overfitting and underfitting, and also what happens to parameter estimates as we add additional terms to the model. Now, if I wanted to fit a penalized model, and I'll simply select Lasso here, and there are other things that we can fit, it'll work in a similar way. So if I click Go, we're seeing what happens as we add terms to the model. And here's my starting point. But what we're doing is we're gradually shrinking a penalty parameter. So we're applying a penalty to the coefficients, and we're trying to shrink those coefficients. And as we're adding terms to the model, we're basically shrinking the magnitude of that penalty parameter. And we get to a point where we have the best value for validation and log likelihood. So we may come up with different results here because of the shrinkage. So essentially, we're biasing the coefficients, and this helps us to deal with some of the collinearity issues. So there are a lot of different options that we can select there. And in the interest of time, I'm going to step forward and go to the formula depot. So the formula depot I mentioned is where we can store competing models, and then we can dynamically compare these competing models. So here I'm looking at, I have a local data filter, so I'm only zooming in on the test set, and I'm looking at model comparison, and model comparison is just an option under the top triangle within the formula depot. And I'm looking at R-square and RASE, which is essentially root mean square error. It's simply adjusted to be independent of the number of parameters in the model, so it makes it possible for us to compare different competing models. And we're looking at average absolute error. And I previously right-clicked on top of this and sorted by, I believe, RASE to put these in order. So my best model with a minimum error for RASE and average absolute error is this neural net model. Notice my second best model is called a two-stage forward. So this is used when we've got interactions where it first tests for, it's going to do two stages. It's going to look at interactions and it's going to look at main effects in two separate steps. So this is my second best model. Now the nice thing about anything coming out of my generalized regression platform, in fact, if we go look at that model, if I run this model, so I'm just going to run the script, and it's going to create a new column in the data table. Any model coming out of generalized regression is simply, in this case, a least squares regression model. So it's got a lot of interpretive abilities. It's easy to understand what's happening with the coefficients. It's easy to explain to others. So if I get results here that are very similar between a really complex model and a very simple and interpretable model, I might choose the more parsimonious model. Now, what do I do with this? From this point here, this is where I can write out the code. So let's say I want to be able to score data directly out of SAS or out of a database, or maybe I want to be able to develop a web app. So for example, maybe I want to write out Python code. So this is what the Python code would look like for this particular model. And now I can embed this in an application and or whatever my production environment is to score new data as it comes in. And we have an example of this, and this is posted in our user community, and I'll just pull it up quickly. We gave a talk in St. Louis earlier in the month, actually in October, and we did the same thing for houses in St. Louis, where we downloaded data from Redfin and we built similar models. So this is a web application that's built using a JMP Python model that predicts housing prices. And it's going through Amazon Web Services. So if you're familiar with Jupyter Notebooks and with this environment, you can take the JMP code and easily build a web app. So if I change, for example, the number of bathrooms and the size of the home and the year it was built, and I pick a given location, if I click the predict button, it's going to give me predicted values. And I can also save out the standard errors so that I can get intervals for this. So that's an indication or an example of what we can do with this code that we write out. So this is continuous response. Now what if I've got a categorical response? Well, the same tools are available. So if I close this guy down, and I'm going to open up this example called credit card marketing, and here I'm looking at whether a credit card offer was accepted or not based on a type of reward that was offered, a type of mailer that was offered, an income level, credit rating, and then a bunch of continuous variables. I'm going to make this data available. There are lots of exploratory things that I did over here. So for example, I did some tabulations to look at differences between offer accepted, yes or no, on all my categorical variables. I looked at a hierarchical sort of structure to help me try to pick out where I'm getting the optimal value for yes. So for example, this is just tabulation where I've added all of the categorical predictors. If I'm using points with the postcard and the income level is low and the credit card rating is low, then the acceptance rate was about 23%. So I can see that there are some combinations that give me high acceptance rates. So I'll use things like tabulate and distribution and the graph builder to help me understand the data. Now this is just logistic regression, so here's what the logistic fit would look like for this model. These are the key variables, and this is without interactions. We can use the ROC curve, and we can also use the lift curve to indicate how good the model is performing. And the way we interpret the lift curve is the proportion represents if we save our model and we sort the predicted probabilities in descending order, and we take, for example, the top 10% of the sorted probabilities, we have a lift of 3, or roughly 3. This indicates that we're capturing 3 times more of the yeses than we would if we just used a random model. So basically, lift is giving us an indication of the capture rate, of how many more of the yeses are we actually capturing based on probability. We can also use the profiler here, so we can see that there's a difference in the acceptance rate for these different predictors. So logistic regression is the same as what we've seen. We can fit a Bootstrap Forest model, a boosted model, so these are all the same. We have a couple of other models that are available. For example, naive Bayes is available. And one thing we'll notice for all of these is if we look at the confusion matrix for all of these models, none of the models are predicting that the offer will be accepted. So the predicted count for yes is 0 for all of these. So if I'm looking at a decision tree for offer accepted and I click go, and I ask for the details, I'm not seeing any that are predicted to be yes. So in the interest of time, I want to move forward and talk about some of these special considerations. So everything we've already seen for continuous data applies to categorical data, but we're predicting probabilities rather than predicting means. So let's say that I have saved a logistic model out to my data table. And when we save a logistic model out, we get the logit. Okay, so these are all the parameter estimates in our model. Then we get a calculated probability of yes and a probability of no. And we get this column that's most likely offer accepted. And what this does is it simply says whichever value the probability is higher, we'll use that as the classification. And this is what's used in the confusion matrix for all of those modeling platforms. So what I want to talk about here is how do we deal with classification where we have unbalanced data? And there are a few different strategies and tools that we can use. There's an add-in called a Data Mining Tools add-in, and I'll make this journal available. And this provides access to a number of different tools. Stratified split balanced allows us to basically build a model where we're balancing our response of interest in the training set or the training and the validation set. And this allows us to do a better job of picking up the signal from those who actually accepted the offer. So this is one strategy. Now another strategy is to change the cutoff for classification. So if I look at the probability of yes, and this is just a distribution of the probability yes, notice that the maximum predicted probability of yes is only 0.34. So none of these models are actually able to use a 0.5 cutoff and classify anything as a yes. So we could use this knowledge. In fact, this translates to what we saw in the lift curve. So with a lift curve, we saw that the lift was 3 for the top 10% of the sorted probabilities. The probability associated with that is 0.13. So if our model has a probability of 0.133 or higher, we're 3 times more likely to capture the yeses. So we can use that to change the cutoff for classification. And to explore this, I've created some formula columns. So I've created columns where I'm exploring different cutoff values. So here I'm indicating if the probability yes is greater than or equal to 0.2, call it a yes, otherwise call it a no. And I've done that for different values. And let me just run a distribution of these. So if I use the original cutoff of 0.5, notice that I'm not classifying anything as a yes. If I use a cutoff of 0.2, I'm classifying 3% as yes. A cutoff of 0.15 classifies 6% or almost 7%. And a cutoff of 0.1 classifies about 0.16%. Now, notice by doing this, we're probably going to classify some that are actually no's as yeses. Now, there's an add-in that does this for us, and this is in that data mining tools add-in, and it's called alternate cutoff confusion matrix, where you can put in a range of values if you've saved the probability formula, and it'll give you the misclassification rate on the validation set across all of those values you use for the cutoffs. Now you can also do this in the column itself. So for example, I'm going to just run, I've saved a formula out, and I'm going to run model comparison. And model comparison is just under predictive modeling, model comparison. So this is what I start with. If I were to look at a summary for my validation set for logistic model, I'm not classifying any as yes. But what if I change the cutoff for classification? So I'm going to right click on this column and go to column information. And under column properties, we have this thing called a profit matrix. And what the profit matrix does is allows us to do two things, either specify cost or change the cutoff for classification. So if I change this cutoff for classification to 0.1, for example, and hit set, notice that it basically backfills the profit matrix. And if I hit OK and rerun this model comparison, now what it's giving me is both the confusion matrix and a decision matrix based on these differential costs. So my misclassification rate when I use this different cutoff is now a lot higher. But notice that whereas before I was classifying all yeses and nos as nos, in this case now I'm also classifying some things as yeses. So some of the nos are now classified as yeses, but now I'm also capturing some of the yeses. So changing the cutoff for classification can allow you to improve your capture rate for those that actually were yeses in this case. Now another thing I can do is if I have true cost here, if I go back to column information for this, and I'll just go back to the profit matrix. Let's say I had true cost here, and I'm just going to wipe this out here. And let's say that I know that if I send somebody an offer that they don't respond to, maybe it costs me $10. But if they actually respond to the offer, let's say that I'm going to earn $500, and there's got to be some sort of context around this, but let's just take this simple example. So now I've got some costs associated with this, and I'm not including the lost opportunity cost here. I'm going to click OK here and rerun this model comparison. Well, now I'm interested in profit, and my average profit per offer is roughly $22. Notice that I've beefed up my misclassification rate, but I'm also capturing most of the yeses. So I'm scoring more of them as no, or I'm classifying more of them, more than no's as yes, sorry, but I'm also capturing more of the true yeses. So if you have differential costs, you can include that in the model to pick that up. So a few ways very quickly of dealing with differential costs and unbalanced data. Now there's also an option for setting the random seed, and this is again within the data mining tools add-ins. You can set the random seed. I use this a lot for validation columns. You need it for neural nets, and there are a few other times when you want to make sure that everybody gets the same results. Now quickly, I mentioned text mining. There is the ability to do text mining in JMP, and I'll just very quickly give you an overview. So we call this in text mining language a corpus, and a corpus is a collection of documents. And in text mining, what we're trying to do is we're trying to pull out information out of unstructured text. So we're trying to get meaning out of a bag of words. So my response here is survey response. We can work in terms of both phrases and words. This gives us the ability to do stemming or regular expression, and you can do custom regular expressions. And I'll just quickly show you what this does. So by default, it breaks it down into terms and phrases. And then everything in JMP is dynamic. So if I want to add phrases because they have extra context, I can add phrases. If I want to be able to combine things because of the same, so for example, cats and dogs or clean up typographical errors, I can recode. And this is the same recode as we get from the columns menu. So if I group these guys together into dogs, now they group together. I've got options for data visualization and cleanup. So for example, maybe I want to stem all terms that have the same base word. So this little dot indicates that they're combined. I can ask for a word cloud. So the word cloud gives me some visuals that allow me to try to understand what the dominant words are. So I'll sort this, say I'll give it a centered view, and I'll give it some coloring. Now this is a survey about cats and dogs, so if I don't want to include information on these categories, then I can add those as stop words. So you get a lot of functionality here, and I don't have time to talk about it, but you can also do clustering or latent class analysis. Latent semantic analysis is essentially principal component analysis. Topic analysis, which is essentially factor analysis. Then I can also do hierarchical clustering on terms and documents. And when I do this, I'm trying to understand if there are themes that are falling out or common groupings. And then I can save those out to the data table. And if I want to build a predictive model, if I've got some sort of a response, now I can use these new columns that I save out as predictors in a predictive model. So very quick view of this. And if you want more information, and again, I'll post this journal. There is a chapter, there's an info kit, and it has a chapter from a book, Fundamentals of Predictive Modeling, and there's also a nice webcast. Now, there are a lot of other tools we didn't have time to talk about. So for example, k-nearest neighbor, indiscriminate analysis, lots of tools for marketing analytics. And I want to remind you that we've provided a lot of resources for teaching and learning about predictive modeling. And I want to pull up just very quickly our website. On our website, we've collected guides and case studies and a lot of other materials for learning and teaching, including data sets and case studies and scripts. So if you're interested in digging in further, you'll see a lot of really nice resources here. So I believe that I am out of time, and I will stop there. Ruth, were there any questions?